welcome to Advanced Quantum Theory. My name is Tobias Osborne, and in this course we will be teaching and discussing quantum mechanics at an advanced level. Another way you could call this course is, instead of Advanced Quantum Theory, you could call this course From One to Many. The principal goal in this course is to take you from the quantum mechanics of a single particle, which you've already met, and apply this quantum mechanics to the theory of many particles. That's our core aim in this course. We're going to take a look at how to define quantum systems involving many particles, and we're going to look at how these many particles interact and what happens after these particles interact. Now, as you can see, I'm videoing these lectures, and I will put these lectures on YouTube shortly after the lecture, and I will send you a link on the stud IP to this YouTube channel, but I think you can already find it just by Googling. There aren't so many advanced quantum theories on YouTube as yet. Let's get to the important things first. So I will say a couple of words about the structure of the course, and then we will get into the topic for today, which is systems of identical classical particles. The structure is going to be 3 lectures and 1 exercise class. There's an additional seminar attached to this course that will take place at a separate time, and for those of you who are interested in the seminar, I will send you an email about those details soon. Now, the way we will be running this 3+1 is that I will do 3 lectures, and then on the 4th lecture time we will have an exercise class, as is fairly standard. Okay, I should say a couple of words about prerequisites. What do I assume you know? I'm going to assume that you know about single particle quantum mechanics. So I'm not going to spend any time in this course talking about the axioms of quantum mechanics. I'm not going to talk about hydrogen atoms. I'm not going to talk about angular momentum. I assume you know all these things. And if you feel like you would like some kind of refresher and reminder of these topics, I cover in the beginning of one of my previous courses, in the first 2 lectures, I review the axioms of quantum mechanics as what I need for this course, and I also say a couple of words about material that's somewhat more directly related to this course. So you can check this out on my YouTube channel. It's the theory of, I think, quantum noise and decoherence. If you watch these videos, you would already have a fairly good reminder of the things that I assume you know for this course. A word about the videoing. Due to European regulations, this camera will stop recording after 30 minutes and it makes a beep. I will pause and have to hit the record button again on my phone, which I'm operating the camera with, to make it start recording again. It can sometimes happen that I don't hear the beep. If you see that I've not heard the beep, please someone tell me, and then I can make the camera record again with this phone here. I'm also taking the sound separately, so the camera will not pick up, this microphone will not pick up discussions in the audience, so you don't have to feel like you have to really whisper if there's something you need to clarify. All right. Now for the actual things that are important for this course, for you guys. The first is the Studienleistung. How do you get it? So you get the Studienleistung if you participate in the exercise classes. It's important that you participate in all exercise classes. If you cannot make it, please contact me. And you will have to hand in all assignments. There will be marked assignments. They will appear on StudIP 1 week prior to their due date. And you are expected, if you want the Studienleistung, to hand them all in and have them graded. For the Prüfungsleistung, it's just an oral exam. Please contact me for an appointment when convenient. Okay, that's to the structure of the course. Are there any questions about the structure of this course? The lectures will be videoed, they'll be placed on YouTube. If you have any questions, please contact me by my email or via the StudIP. What percentage of the assignments do you have to get right to get the Studienleistung? I'm not going to set a percentage. I want to see you if you want to hand it in with your name on it and nothing else, you're welcome to do that. However, I expect that you'll attempt the assignments. They should be pretty easy. I'm not setting them at research level questions. They should be just... I see no reason for you not to be able to pass the assignments. Good. Let's come now to the source material. What can you look at beside these lectures? Okay, I'm basing this course principally on, let's say, 3-4 books. The first book, which covers second quantization, is Volume 2 of Bertelian-Robinson. I will get more to the actual subject matter in a moment. We will be covering scattering theory and following relatively closely the book of Taylor, and also the books of Reed and Simon. I think it's Volume 3. In any event, it's good to have Reed and Simon nearby. And for the final part of the course, where we will cover relativistic quantum mechanics, we will use Weinberg's book on quantum theory of fields, Volume 1. Weinberg's now got many books, so it's important to specify which one. Okay, we're also going to, for the beginning of this course, I'm going to follow relatively closely a paper by Linus and Meerheim, which is in the journal Il Nuovo Cimento, Volume 37, 1977. That's the source material. If you obtain the source material and read through the chapters, it'll be pretty clear which one I'm following. Then you'll have a good background material for every lecture. There will be all kinds of extra things along the way, but these are the main source materials. Okay, here's a short outline now of the course. What do I expect to cover in this course? Well, we have the main core aim is to go from one quantum mechanical particle to the description of many quantum mechanical parties or particles. And therefore, for the first part of this course, we're going to cover the topic of identical particles. And this will take maybe a third of the course. We will go into this in some detail. First, we'll study the classical case. And then we'll study the quantum case. Then we'll cover second quantization. And finally move on to the commutative anti-commutation relations and the canonical anti-commutation relations and the canonical commutation relations. So that'll be the first major portion of our course. Will be focused on identical particles. Then we'll move on to the topic of scattering theory. How do two particles interact and then fly apart? What's the connection between their incoming momenta and positions and their outgoing momenta and positions? And here we will look at, again, beginning at the classical case, we will look at in and out states. We'll look at Möller operators, the S matrix, Green's operators and T operators, and stationary scattering states. For this part of the course, we'll be following the book by Taylor, principally as a guide, using Reed and Simon to refer to the rigorous results. And for this discussion of identical particles, I'll mostly be following Bertelli and Robinson, although that goes into far too much detail for this course. And the final topic will be relativistic quantum mechanics. Here we'll be looking at quantum Lorentz transformations and Poincaré transformations and Wigner's theorem. So the idea of this course is to take you from your knowledge about non-relativistic single particles and bring you up to a level where you can commence the study of quantum fields in earnest, relativistic quantum field theory. So I expect in this course you will learn how to deal with many particles that interact in high energy regimes where relativistic effects become important. That's the principal goal for this course. And after you finish this course, you'll be really well prepared to study quantum field theory, relativistic quantum field theory, and then on to things like string theory after that. Additionally, this course is absolutely vital if you want to study condensed matter physics or solid state physics. These are systems which also comprise many, many, many identical quantum mechanical particles. All right, so I think that's all I need to say about the structure and the source material. Before we get started, are there any burning questions about these topics? Very good. So you probably encountered quantum mechanics, I guess, some 2 semesters ago, some of you, yeah. I mean, I guess you've been aware prior to then that there's this thing called quantum mechanics and that it's quite mysterious. So one of the reasons that quantum mechanics is extremely mysterious is that we perceive the classical world, and that's where our everyday experience comes from. It comes from interacting with the classical world. But the quantum mechanical rules that govern this universe are not directly leading to the classical, to the way the classical world behaves. So I'm going to schematically give you a picture of why quantum mechanics is hard. Okay, here's a circle. This is meant to represent the space of all quantum theories. Now, what's a quantum theory for the purposes of this course? Well, it's a pair of a Hilbert space and a choice of a Hamiltonian self-adjoint operator on that Hilbert space, the generator of time evolution. And the space of all quantum theories is the space of all pairs, if you like. That's one not particularly rigorous way of describing the space of all quantum theories, but I think it's sufficient for the purposes of this course. So this is a big infinite set. There's lots and lots of points here. You've got to think of each point as being a pair of a Hilbert space and a Hamiltonian. But we don't directly perceive all the building blocks of a quantum theory. Instead, we perceive the universe after it's experienced decoherence and dissipation. The only observations we can make are typically high, large energy relative to the fundamental constituents of these quantum theories, relatively large, coarse-grained, high-energy measurements. In other words, we can't measure everything. And furthermore, each quantum theory that governs a system we're interested in interacts with an environment and experiences dissipation and decoherence. So what we typically see is an effective classical system that models what we can observe. And this process where we get an effective classical theory that describes the things we can see, that is a result of decoherence and imperfection of our measurement apparatus. And the process of selecting out that classical theory which best models the things we can measure, that's called the classical limit. Now, the classical limit has been interpreted by many authors in many different ways, but for the purposes of this lecture, the classical limit is the result of decoherence and imperfect measurements. I'm not going to say particularly very much about either of these processes in this course. That's a topic better suited for a course on quantum noise and decoherence. And after you take into account the effects of decoherence and imperfect measurements, you've ended up with an effective classical theory that best models what you can observe. And what's the space of classical theories? Well, each point in the space of classical theories is a phase space, which I'll just write as a little m, and also a Hamiltonian, but a classical Hamiltonian. So the reason we perceive the classical world is because of decoherence and imperfect measurements. And when we want to quantize something, we're trying to solve a problem, and it's a very ill-posed problem. The quantization, the process where you take a classical theory and invert this map to work out what quantum theory led to it, that's an example of a kind of inverse problem. Quantization is the task of inverting the classical limit. And the reason it's mysterious and hard is that it's not well posed as a problem. The reason it's not well posed is there exist pairs of quantum theories which have the same classical limit. They may have the same Hilbert space, but different Hamiltonians, for example. Or they may have different Hamiltonians. They may have different Hilbert spaces even. And they might still be effectively well modeled by the same classical theory. It's even worse. You could even have quantum theories which have more than one classical limit, depending on how you define the words classical limit. So altogether, the process of taking the classical limit is not particularly well posed to begin with, but certainly it has the property that more than one theory can land on the same effective classical theory. And when you have a map that takes many things to one, then you're in for trouble when you try and invert that map. That doesn't mean it's impossible. It just means that you're in for trouble. And to give you a good example of where this happens in our everyday experience, just think about security camera footage. This is my favorite example. When you watch Ort or something similar, you see the security camera footage of the perpetrator, and it's all blurry and messy, and you can't make out the perpetrator's face, but they hit this button, right? This enhance button. And then, poof, you have this beautifully crystal clear picture of the perpetrator. Now, what they're doing there is inverting a many-to-one map. It's a noisy map that takes two initially different configurations and produces something that's approximately the same. It's not impossible to do this, but you need some kind of hypothesis to make that work in practice. And that's exactly what we do in quantum mechanics when we quantize a system. We know the universe is quantum mechanical. I mean, it didn't become quantum mechanical in 1927 at the Solvay Congress. It's always been quantum mechanical, and the only problem we have is that we perceive this classical world of Newtonian objects, and we're trying to guess which quantum theory is the right one that leads to this classical world after decoherence and imperfect measurements are taken account of. And the hypothesis that allows us to simplify this task is usually symmetries. We usually have at our disposal some extra knowledge. We know that the classical theory has some symmetries, and we expect the original quantum theory to also respect those symmetries, and that makes our life a lot easier. Symmetries assist in the task of quantizing. Without symmetries, life would be so much harder. And I'm going to tell you a lot about one particular symmetry in this course, and it's called the symmetry of identical particles, or particle exchange. It's a fascinating subject to invert this map, especially since this map isn't particularly well defined. So I think it's an ongoing program in physics. In fact, in some ways, you can think of this as physics itself. In physics, you always have access to noisy statistical data from your experiments, and you want to use that data to infer a hypothesis about what's going on. The problem is you can only reject hypotheses in statistical experiments. So the best you can do is not get the right hypothesis, but to carve out the wrong hypotheses. And the ones that remain, well, they're the ones you think that are the quantum theories that govern the universe. Or maybe it's something even more than quantum theory, we don't know. At the moment, quantum theory is the best hypothesis we have for how the degrees of freedom of the universe evolve, but it might be that as we make better experiments, we find a better theory. I won't say anything more about this. So symmetries, and that's where we're going to commence our discussion in this course. An organizational question comes to my mind. The timing of this course is not particularly perfect when it comes to lunch. Is there any preference to whether we start early or finish late? Would everyone here in principle be able to get to this lecture by 12? So ST instead of CT. Okay, if anyone has a problem, just let me know, because we might start ST so that you can have lunch at least at 1:30 or a bit earlier. Good. Identical particles. Why am I talking about identical particles? Why am I talking about exchange symmetry? That's the question I want to answer to begin with. Why do we think particles in nature are identical? Well, the answer comes in the form of something known as the Gibbs paradox. What does the Gibbs paradox say? It says that if you have a gas of an ideal gas in a container at thermal equilibrium, and you put a barrier in the middle of this container, then the entropy decreases. Let me just draw a picture. So we have some ideal gas, thermal equilibrium. Here they are, the particles bouncing around in this container. And if we place a barrier at some instant of time into this container, I'm trying to render this picture as identical as I can to this one. We put this barrier in there, then the entropy of the gas is reduced by adding the barrier. Unless the particles are identical or indistinguishable. So this would be bad, right? If you could put barriers in boxes and reduce entropy, then you're on your way to a good violation of the second law of thermodynamics, and infinite wealth, fame, and fortune awaits you. So it's only a paradox, however, if the particles are not identical. So because we don't observe this in nature, in our systems of ideal gases, we've come to the conclusion that particles are actually identical. Thus, we ought to think about the configuration spaces of identical particles. So this is what we're going to talk about now is classical theory, or the theory of classical identical particles. We're going to talk about the theory of systems, classical systems of identical particles. Now this is, according to the picture and the motivation I have at the top there, this is a slightly backwards way to do quantum mechanics. You know, the correct way, according to what I just said up there, to do quantum mechanics is you study quantum mechanical systems and then take their classical limits until you get the right one. So why bother studying classical systems of identical particles at all? That's a good question to ask. And the answer is that I want to promote here is that it gives us an intuition about what classical limit we want to get. Also, it's kind of interesting as a topic by itself, as you'll see. Mathematically, there's some surprisingly subtle structures that come out. But usually when you study a classical system, when you're thinking about quantum mechanics, the reason you're doing it is because you want to work out what is it about this classical system that I want to be present in the quantum theory that has this as its classical limit. It's always a mouthful to say these sentences, which is why people say things like, we just want to quantize identical systems. But I'm going to stress over and over in this course, quantizing isn't well posed as a question by itself. You just got to always think of it in the context of a classical limit. I think you could be forgiven for thinking you already know about the classical theory of identical particles. I mean, how hard can it be, right? You just have more than one particle. Isn't it just like phase space of n particles? Well, the answer is yes, but not quite yes. So let's begin with a system of identical particles, of identical classical particles. And let X be the configuration space We're going to assume we're going to have multiple numbers of the same kind of particle, so we've got to talk about that particle to begin with. So we let X be that configuration space. Now, it could be Rn, it could be some discrete set, it could be some measurable set, it could be anything, right? At this point, I'm not saying anything about X other than it's at least a set. Something, it's a set. And then we assume we have n indistinguishable particles moving in this configuration space. And we want to understand what's the configuration space of n indistinguishable particles moving in X. How would we describe that as a set? So the naive answer, and I think that it's very logical to say what I'm about to say as a proposal for the configuration space of n indistinguishable particles is, why don't you just take X, the Cartesian product of X n times? Right? That's a very natural thing to say. Once you've said where each particle is, then you've said where each particle is. except, right, you've said too much. Because certain configurations are exactly the same physically, because these particles are indistinguishable. So saying that particle 1 is at position 1 and particle 2 is at position 2 is exactly the same as if particle 2 was at position 1 and particle 1 was at position 2. There's a symmetry there, and we've got to take account of that. There we go. There's no distinction between the configuration of n particles x1 through to xn and any permutation of those coordinates. They both refer to exactly the same physical situation. So they're equivalent. And what we're going to do is exploit this physical equivalence relation to build a smaller configuration space that captures exactly the data we need to specify n identical particles and no more. We're going to build an equivalence relation on this candidate configuration space, xn, which correctly captures this overcounting that we have, or this overspecification we have in this system of coordinates there. So we're going to identify x and with y if y is some permutation of the coordinates in x. You can check that this satisfies all the conditions to be an equivalence relation. And what we're going to do is we're going to take this equivalence relation, we're going to take the quotient of xn by this equivalence relation. And that is going to be our configuration space. So this is hereby a definition. The configuration space of n identical particles moving in X is called M, and it's X to the n modulo this equivalence relation there. May not look like much, but if you know about topological spaces, you should be thinking, whoa, quotients. Quotients do interesting things to topological spaces, often uncontrolled and strange things. And this case is not an exception. One of the things a quotient usually does on a nice smooth topological space is introduce singularities. And to get an idea of what I'm talking about here, imagine you have a piece of paper. You cut out a wedge. Make that wedge, say, 60 degrees, a 60-degree wedge out of let's say, an infinite piece of paper. But you can do it already with a piece of A4 paper. You cut out a wedge and you identify the points on one side of the wedge with the other. You set up an equivalence relation. So that glues the paper together, and I'm not going to be able to do this without actually cutting the paper, so let's do that now. There you go. So you start out with this space. It's got a boundary, but it's not particularly nasty. And then you glue along this edge here. That's an equivalence relation. And now you've built a new space. And the thing about this space is there's a conical singularity here. And this is the source of some very interesting physics indeed, as we'll see. Because this example wasn't chosen randomly. This will turn out to be relevant in 2 dimensions. What can we say about M? Well, there's some general things we can say about M. The first thing is a consequence simply of the fact that Sn, the symmetric group on n symbols, is finite. I mean, it's got n factorial elements. That's a big number, but it's still not infinity. So that means that if x is r to the n, which is standard configuration space that we care about for most of non-relativistic quantum mechanics, then we know that M is locally isomorphic to just xn. What does locally isomorphic mean? Well, in a physical picture to have in mind here is imagine n particles just not being near each other, n particles each in their separate little neighborhoods. Then the configuration space of n particles which aren't near each other is just locally the same as if the other particles weren't there. So it's just n copies of Rn. It's only when the particles come together that strange and interesting things can happen. And when the particles come together, we have examples of singularities, conical singularities. And I want to go through some pictures of M for different spaces. And the first space we can think about is just one-dimensional space. I have enough room. Okay. All right. The simplest, pretty much the simplest example we could contemplate is one-dimensional space and two particles. Right? So X is R1, and we've got two particles moving on the line. So I'll draw the picture of X to the power 2 in this case. Well, we know what X to the power 2 is, it's just R2. And now we've got this equivalence relation. So what's this equivalence relation saying? It's saying that the configuration x1, x2 is the same as the configuration x2, x1. I'll move this up for you. X1, x2 is the same as x2, x1. Now that transformation here, going from that to that, is a reflection about this axis here. So if I have a point here, say, then there's another point in big X2 that's equivalent to that point. And that point you get just by reflecting through this axis here. I'll do it sort of closer here. So there's its partner there. These 2 points are equivalent. They're the same one. And there's always 2 ways to deal with spaces with equivalence relations. Either you deal with the overspecified space x2 and always remember that these two configurations are the same, or you spend the symmetry, if you like, throw out these points because they're physically identical, and just focus on a representative of each equivalence class. So the equivalence classes here for this space, what did the equivalence classes look like? Well, they're just tuples, right? They're just pairs of pairs. When we take the quotient of the space by this equivalence relation, we could either always remember that we have these pairs are always the same point, or we could pick a representative. And you want to, how do you pick a representative in a unique way? Well, you have to find a way, right? You have to find a recipe to always choose exactly one point from an equivalence relation, equivalence class. Now, there's one way that I hope sort of pops out in this example, as the best way to pick a representative. I mean, there's no magic formula, but you pick the one which you like the best. And the one I like the best here is that you always make sure that x1 is strictly less than x2. So that always picks x1 is less than x2, right? So it's always going to pick this quadrant here. Yeah, so if this is 1, 2 here, and this is 2, 1, this recipe here of choosing a representative for each of these equivalence classes always selects this point here and says we're not going to consider this point. And so we throw this out. And you can visualize, therefore, the space of two identical particles moving in R1 as being the lower half of this two-dimensional plane, like this. And then you can see already the statement about M being locally isomorphic to Rn cross Rn, so on. Here it's true, right? Any point in the interior of this space is locally isomorphic to R2. There's a little open neighborhood of each point here, which is diffeomorphic to R2. So this is certainly, that point is correct. However, there's something funny, isn't there? Because if we have a configuration and this system of two particles undergoes this trajectory in configuration space and touches the boundary, then some funny things can happen. And it's got to do with the velocity vector. So that's a perfectly legal trajectory in this quotient space. But you've got to be careful, because as you get close to the boundary, your velocity vector undergoes a reflection. So the velocity vector is a tangent vector. So this is just motivation for what's coming. So you have a tangent vector to this curve. And then as you get closer to the boundary, your tangent vector undergoes a reflection at that point there, at the boundary. Yep.
Just one quick question to make this consistent. I think the x2 should be smaller than x1 to make it consistent with the sketch.
You think x2 should be smaller than x1 to make it consistent with the sketch? Ah, right.
Or just rename the axis in the sketch.
Shall I rename the axis in the sketch, or shall I change? Yeah. Sorry about that. x1, x2. So although trajectories in configuration space seem perfectly compatible with this boundary, we know, this is a warning, that velocity vectors, which are tangent vectors to this manifold, do undergo funny transitions at the boundary. We have to be careful about that. And we're going to get into this a little bit deeper as we go through this theory of classical particles and try and make this more quantitative. Yep, the question?
Is there a mathematical reason why we not include the line, the points x1 is equal to x2, or is that a physical constraint that two particles can't be at the same point? Because mathematically they could be in space, right?
That's a very good question. Is there a reason why I appear to be excluding the line x1 equals x2? There's two answers to that question. One is you could take the point of view that two identical particles can never share the same location, which is what I'm doing in this picture here. And the other is that you allow that as a possible configuration. Both are actually legal ways to proceed. There's no particular way to prefer one over the other. For the case of this example, I preferred that two identical particles would never be allowed to share the same location. But if you have a good reason, a good hypothesis to allow that, then by all means proceed with that hypothesis. In which case, you would change that condition to that. And you would include in that dotted line the actual line. So the answer is, it depends on what you think the system will do. We typically don't allow particles to occupy exactly the same position. But I'm not going to forbid that and say that that is wrong. Just don't think that we need to deal with that configuration. So generally, much of this discussion could be framed in terms of particles moving on arbitrary spaces, but I'm going to just fix on Rn pretty much from now on. But you could take everything I said today, you could even make this an exercise, and extend as much as you can to the case where X is a general set. So whenever I say generally, I mean actually more specifically. So this is, be aware of this misuse of language. If X is R to the D, we're going to introduce a coordinate system that's particularly well suited to explaining the properties of our space M. We're going to introduce some coordinates called center of mass coordinates. Set up a variable x subscript cm. Like that, and we will leave the rest unspecified for the moment. Now the nice thing about center of mass coordinates is that if you, there's d of these, right? D of these coordinates. Is that they're invariant with respect to permutations of the particles. So this allows us to separate off some of the dependence of M on some of the coordinates. I apologize, I've been using Rn up to now, and now I'm using Rd. I'll try and stay consistent. So there's little n and big N, and D I want to say. There. So we're going to separate off this dependence on these nice symmetric coordinates here. And that allows us to isolate the weird singular stuff into this other part of the manifold, which we're going to call R big N little n. And these contain all the relative coordinates. This Rn little n is the relative space of all the other degrees of freedom. We haven't said what they are yet. All we could say about this relative space at the moment is that it's got locally little n times big N minus n dimensions, and that it's not a differentiable manifold in general. It's an example of a thing called an orbifold. And I'm going to just assert what structure this manifold has for the remainder of this lecture. And in the next lecture, we will look what the quantum mechanical consequences of this observation are. What can I say about R little n big N? Well, we're going to try and understand R big N little n, by studying just two particles. It turns out this is an extremely complicated space in general. There's some things we could say about it, but in general it's a very complicated space. And in fact, already the case of two particles, namely big N equals 2, is enough to expose some quite interesting structure. So this is for the case little n is arbitrary. So what are we doing? Well, we have to identify, to build this space, relative space, we're always identifying x, which is x1 minus x2, with minus x, which is x2 minus x1. To build R2, little n, we're always identifying this relative coordinate x with minus x, same coordinate. There is one singular point at the relative coordinate equals 0. And we're going to subtract that point off, the singular point. I'm always going to focus on the case where the two particles are never allowed to be on the same spot. So separating off that point, it turns out that the relative space is isomorphic to R plus Cartesian product Pn minus 1, and this P here is real projective space. So I'll explain what that is in a minute. Well, For most values of little n, it's real projective space, but for some it isn't. So R, this R plus part here is just like the so this R plus part of the parameterization here, this is just the length of the relative coordinate x. And we can list what this Pn minus 1 is for various values of n. So for P naught, it's just a point. So in the case n is 1, 2 particles moving on the line, then actually R2 comma n minus the 0 relative coordinate is just R plus. So that's easy. P1, 2 dimensions, it's a circle, the relative coordinate. The relative space is isomorphic to a line, half line crossed with a circle, which is otherwise known as a cone. And Pn minus 1, in general, for n bigger than or equal to 3, is a doubly connected space which we can identify with real projective space. And I'm going to draw you a picture of 2 dimensions in a second, and then we'll end with that. So I just want to make some comments about this relative space R2 comma n for various values of n. The easy cases, life is easy for us when n is 1, because there it's just a point, couldn't get easier. And it's easier for us when n is greater than or equal to 3. So we live in apparently 3 spatial dimensions, maybe 12, we don't know, maybe 11, maybe an infinity. We don't know how many spatial dimensions we live in, but it's probably more than 2. However, something really super interesting happens when we have particles constrained to move in 2 spatial dimensions. There, this space is a circle, and the circle's not simply connected. So there's some interesting possibilities that can arise in 2 dimensions. We're going to dwell on those possibilities a little bit in this course because they've become recently very relevant to physics, to physical experiments, because we've managed to design materials where the quasi-particles are confined to live in 2 dimensions, and these particles are logically allowed to behave in ways that will sense this topology here of the circle, and we are just on the cusp of measuring these particles, and these particles have a name. They're called anyons. We're going to learn more about these as we progress in this course. So even though we don't live in 2 spatial dimensions, we can simulate 2 spatial dimensions and see some of the strange properties of this relative coordinate space, both classically and quantumly. But classically, it turns out to be a bit boring. So it's the quantum case where it gets super interesting. And the fact that this is doubly connected will turn out to have huge consequences for quantum mechanical systems. It gives us 2 possibilities for how identical particles can behave, and we give these possibilities names. The names are bosons and fermions. So in 3 dimensions and above, already these considerations here will have consequences for the properties of identical particles. We will learn that there's only 2 types, bosons and fermions, in quantum mechanics. It's a direct consequence of this observation here. Yep?
I don't understand what you mean with doubly connected space.
I will define that later.
Okay.
Yeah. So this is, you can of course, we'll get to the definition of that in the next lecture. At the moment, you can just assume that doubly connected is some property that has the consequence of there being 2 of something. Roughly speaking, if you go on a circuit through your manifold that traverses the manifold twice, you can always contract that circuit to a point. But if you go on a circuit through your manifold that only goes through it once, you can't always contract it to a point. That's the hand-wavy definition of doubly connected. We'll get a clearer one next lecture. And you can see that the circle doesn't have that property. If you go around the circle once, you cannot contract that to a point. If you go through it twice, you cannot contract it to a point. If you go through it 3 times, you cannot contract it. They're all just different. They're homotopically different trajectories through the configuration space. So yeah, we'll end with 2 particles in 2 dimensions, and I'll just give you a picture for what this relative space looks like. And then next lecture we'll look at we'll begin the quantum mechanics, yes we will, of these systems. Actually, before I do that, this is all predicated on particles being point-like. So nobody objected when I said particles were points. And in fact, there was a reason for that, because when we look around, particles look pretty point-like. But it's emerging, this is still very much current literature, very exciting research, that logically it's possible for excitations in systems to be membrane-like. And then things get tremendously more complicated. If you think about the configuration spaces of one-dimensional strings or membranes, then already at a classical level, things are really much more deeper and subtle than just for points. That will take us a little bit too far from our course, I'm afraid. Let's just deal with the next simplest example. So M, the configuration space of 2 identical particles moving in R2, is isomorphic to R2 Cartesian product R2 modulo this equivalence relation. And according to what I just said, that's the same as R2 cross this relative space. And R2, comma 2, it's an exercise. Not a difficult one. I'm going to write out the answer, but the exercise is more to parse the answer. So this relative space is where you remove the origin of the plane and identify R2 x with minus x. I'm going to draw you a picture of this space. It's well, I hope I can render it nicely. You'll see the problem in a second. It's a cone. It's a conical space. So if you think about it, this is a puzzle, right? This picture is a puzzle. It's not an explanation. If you think about the 2-dimensional plane where you punch out the origin and you identify x with minus x, so you've got to think about that, right? Here's the piece of paper. I punched out the origin, and x up here is always the same as minus x there, inverted through the origin. You've got to think about what does that look like. And it looks a bit like this cone here. So So there's an exercise which is confirm this picture. Have I drawn it correctly, or have I misrepresented this picture? Good. I think we'll stop here and commence next lecture with parallel transport and velocity vectors. Okay. Thank you very much.